Okay, so what we're going to be doing these next 2 days is we're going to be talking about Bohr's model of the atom before we get into the electron configuration. So this is just a little bit of review when it comes to placing the electrons in orbits. And so you should have learned this in integrated your freshman year. So this is a bit of a review. So go ahead and follow along. So your objectives is Bohr used data from atomic spectra to propose planetary models of the atoms, in which electrons orbit the nucleus like planets around the sun. So atoms are usually at a ground state where the electrons occupy orbitals with the lowest available energy. Atoms can become excited when the electrons absorb a photon or an energy particle with the precise amount of energy to move the orbit or to an orbital with a higher energy. So atoms exist in an excited state for a short period of time, and valence electrons are responsible for the chemical properties of elements, okay? So just a little review. So atoms have a nucleus that contains protons and neutrons. So just remember, that's at the center of the atom. So if we were to compare it to our solar system, our sun is the center of the solar system. So you could think of our sun as the protons and neutrons in an atom. Electrons are contained in shells that actually surround the nucleus. So kind of like planets around the sun and they have their different orbits, okay, electrons follow the same pattern. So an atom is made up of mostly empty space, and that was due to Rutherford and his gold foil experiment. And so we know that. And protons have a positive charge. Okay, and the reason being is in Rutherford's model, the alpha particles, which had a positive charge, were deflected. So it only means that there had to be another positive charge that was pushing it away. And then electrons have a negative charge. Neutrons are also neutral. Okay, so those are some things that you should have reviewed. And when we are taking our quiz on Wednesday, this is going to be some of the material that you're expected to know. So when we talk about electron placement, electrons are kept in an atom through electrostatic attraction. Okay, so the positive nucleus attracts the negative electrons. Okay, our electrons would want to repel each other because they're near in orbits. Okay, but the reason they're not repelling each other is because of the positive particles at the center of that nucleus. Okay, so if Rutherford's model in the work of classical physics were correct, okay, because we have a positive particle in the nucleus, so there's positives here, the electrons would be attracted to it and should eventually collapse into the nucleus, but this doesn't happen, okay? So electrons would lose the energy and spiral into the nucleus because of the attraction of the positives and the negatives, okay? So just think of like a magnet. If you have a positive side and I put a negative up to it, it's going to attract. If I put another positive to a positive, it's going to repel. So these are just electromagnetic attractions. So how did Bohr fix this problem? Well, he said electrons are in quantized orbits. Okay, so each orbit requires a fixed clump of energy, or quantum. Okay, quantum just means energy. So no electrons can be in between orbits. The idea of a quantum is based on the energy that's based on Max Planck. So what he was saying, Bohr said, well, you have two energy levels here. Okay, and there's more energy levels, but for this example, energy level 1 has less energy than energy level 2, and so on. Energy level 3 would have more than energy level 2. Energy level 4 would have more than 3, and so on. Okay, so what he was saying is they had to be in fixed orbits. They couldn't be in between orbits. Okay, so it could be on the first energy level. It could be on the second energy level. It could not be in between. All right. So electrons must gain energy. Okay. And how they do that is they absorb a photon. And when they absorb energy, they actually move from a lower energy level to a higher energy level. So it could go from 2 to 3. It could go from 2 to 4. It could go from 3 to 4, 3 to 5. It would go from any energy level to a higher energy level. That's when it gains energy. When it loses energy, an electron would actually drop energy level. So it may be at energy level 5. It could drop to a 3. It could drop to a 2. Okay, so as long as it's going down in energy level, it's actually emitting a quantum of energy. Okay, so each orbit is definite and it's a fixed pathway. So the further from the nucleus, the more energy an electron has. So if you were to compare these 3 electrons right here, okay, the electron on the outside has a higher energy because it's in a further energy from the nucleus. So the electrons must gain a photon of energy to move to a higher orbit. So basically a light particle. So we see a light particle coming in. It's going to hit this electron. And notice when it does, that electron absorbs the energy and it moves to a higher energy level. So we call this an excited state. So when the electron goes from a lower to a higher energy level, in that higher energy level, it's considered, and it's excited. Okay, it's gained energy. Okay, so think about it. When you guys have energy, you're excited. Okay, electrons are the same. Well, on the opposite, an electron must lose a photon of energy or a light particle to fall into a lower orbit. So notice it's in the second energy level. And then we notice it goes to the first energy level, but it also emits a photon. Okay, it emits a light particle. Okay, this is where we call an electron in its grounded state. All right, so when an electron's at its lowest energy level, it's at its ground state. And we can actually see photons of energy in this part. Okay, so when an electron goes from a higher energy level to a lower energy level, it actually emits light. And we see that light as color. And now depending on how far it dropped, it could give a different spectrum or wavelength of energy, giving, we could see as Roy G. Biv. Okay, so obviously red is the lowest energy level. Indigo is the highest energy level. And so in between, obviously, they would be anywhere in between those energy levels. So just to reiterate it, when the electron falls down into the lower orbit, it releases a photon, which we see as color. And then when it absorbs an energy level, the electron actually jumps to a higher energy level. Ooh. Now, problems with Bohr's model is it only explained the chemical behavior in the atomic spectrum of a hydrogen atom. Reason being is because there's only one proton and one electron. So it was very easy to explain what that one electron was doing. All right. So what you're going to need to know is looking at the periodic table, each electron shell can hold a certain number of electrons. And we're going to learn more about this when we get into periodic trends. Okay. So the first energy level that we would have would only hold 2 electrons. It would go 8, 8, 18, 18, 32, and 32. Okay, so you need to make sure you're writing this. All right, so each shell can hold a certain amount of electrons, which we see. Now, the electron shells are filled from the inside out, meaning I have to fill energy level 1 with 2 electrons before I can fill energy level 2. I would have to fill energy level 2 with 8 electrons before I could move to energy level 3, and so on. Okay, and so just think about it. As you get further from the nucleus, you actually have more space to hold electrons. That's why as we get further away from the nucleus, okay, so think of the nucleus, and I'll go ahead and give you guys a, so if we're looking at this, well, as we get further away, you can see there's more space to be held for electrons. So that's why the pattern we see is as we get further and further away from the nucleus, we can hold more electrons. And so noble gases have full outer electron shells. Okay, and we'll be talking about this when we get into periodic trends. So valence electrons are electrons in the outermost shell. All elements want to fill their outer shell with 8 valence electrons. This is what we call the octet rule. So my period equals my number of shells. And then my group number is my number of valence electrons. And so I'm going to briefly explain this in your the next video that I'm going to have you guys watch after this. Okay. So number of valence electrons. Group 1 is right here. Group 2. Then we have 3, 4, 5, 6, 7, and 8. Okay. And so that's just for the first 3 periods. So this is period 1, period 2, period 3. Okay, so what I would actually want you guys to do is just Google periods on a periodic table and groups on a periodic table. Okay. So how many valence electrons does the following have? Well, if we look at aluminum, aluminum is in group 3 right here. So it's going to have 3 valence electrons. Carbon has 4 valence electrons. Bromine has 7. Silicon has 4 because it's in group 4 as well. Neon has 8. Lithium has 1. Phosphorus has 5. Okay, and so what I want you guys to do is go ahead and watch the next video that is actually attached to the link to go ahead and draw a Bohr's model. Okay, and then I'll briefly introduce how to explain how many electrons are in each shell.